In this video, we'll be really diving into talking about zeros and what it means about their multiplicity for polynomial functions. So, to start with, zeros of polynomial functions actually have a lot more depth to them than we have seen so far. Namely, a polynomial function of degree n has at most n real roots. This comes from the fundamental theorem of algebra, which we'll see in a couple more sections. Actually, it's about 3 more sections, I think. But furthermore, we'll also can see from looking at them that the graph of a polynomial function of degree n has at most n turning points as well. These are also called relative extrema, and these are things, it's these parts, right? And actually, it's not n, it's n minus 1. Sorry, I messed that up. But, for example, moving on, just kind of see this, the function f of x equal negative x to the fourth plus 2x squared can thus have at most 4 zeros and at most 3 turning points. We have also already seen that for polynomial function f and any real number a, the following are actually equivalent. First off, x equal a is a zero of the function, but what that means by definition is x equal a must be a solution of f of x equals 0. But it's not too hard to see that since we're talking about polynomials, that then x minus a is a factor of f of x, okay? So we can always pull that out. But then, another thing, graphically, what all of this would mean is that the point a comma 0 must be an x-intercept of the graph of f. So for example, let's try finding a polynomial function that has the given zeros, 4, negative 3, 3, and 0. Well, if those are all zeros, we want to build a polynomial function that has those. Well, we can look here and say, oh, well, we know x minus a is a factor, x minus 4, x minus negative 3, x minus 3, and x minus 0 must all be factors, right? So, we have, by the correspondence between these two, between 1 and 3, we see that these will be zeros if and only if these are actually factors, okay? X minus each of those is a factor. Namely, we have x minus 4, x plus 3, x minus 3, and x minus 0, which will just be x. So by multiplying all those together, we actually can get our polynomial. I'll go ahead and write it this way because this is a little easier to see, times. So we have our f of x equals that. X minus 4, then we have x plus 3, x minus 3. Putting each of those together, that will give me x squared minus 9. This will give me x squared minus 4x times x squared minus 9, and then we need to FOIL that out. FOILing that out will give me x to the fourth minus 4x, so outer, minus 9x squared. So minus 4x cubed, we'll go ahead and do that first. Then we'll do minus 9x squared. And then we'll do plus 36x. Okay? So if you were to actually go back and factor this, you would end up with this, right? And this illustrates the point we said before, which is we had a degree 4 polynomial, and we had 4 different zeros. So now let's have you try an example. Go ahead and try to find a polynomial function that has the following 2 as zeros. It's also helpful to go ahead and check your result with the quadratic formula. On the count of 3, I'll reveal the solution. 1, 2, 3. So here we have that our factors using the equivalents of 1 and 3 on the previous page. That our factors are x minus all of that, well, the negative distributes giving us that, and x minus this, which distributing changes the sign here. We then have that f of x should be a polynomial function that has those as zeros should be a multiplication of those two factors. Here, FOILing out, we see that distributing x through all of that gives me that. Distributing negative 1 through all of that gives me this line. Distributing negative root 2 through all that gives me that line. things cancel, and I end up with this. Well, I can check that. If I solve for the zeros of that, I should get these two. Well, using the quadratic formula, I see that by plugging in and simplifying, I actually do get 1 plus or minus the square root of 2. But there is actually still more that we can say. Namely, a factor x minus a to the k, where k is greater than 1, yields a repeated 0, x equal a, of multiplicity k. And this is useful for a number of reasons, most notably for graphing. That is, when k is odd, the graph crosses the x-axis at x equal a. You'll want to go back and see a couple of pages ago the correspondences, because remember, x equal a is going to have to be an x-intercept since it's a 0, namely x minus a is a factor, right? And furthermore, and this is far more interesting, when k is even, the graph only touches the x-axis, but it does not cross the x-axis at x equal a. In other words, this creates a turning point, okay? Because it would look something like this. So when it was odd, something like this could happen if this is a, or it could be something like this if it's a, or it could be something like this. It could like level off, right? At a, okay, if that's a. However, if it's even, one of two things happens. You look at a, it either comes down and just touches right there, or it comes up and just touches right there. And we saw this a lot with our even functions in the last, in our even power functions in the last section. So, for example, if we look at this problem, let's see, let's look at its zeros first. If we look at its zeros, we can factor out negative 2x squared out, and we have that we'd have x squared plus 1 left over, or x squared minus 1, sorry. That will give what as zeros? Well, this can factor as x plus 1, x minus 1, and then we have x squared and negative 2. This creates x equals 0, which is a 0 of multiplicity 2. And then we have x equal plus or minus 1, which are both multiplicity 1, right? So it's not, in other words, not repeated. So not repeated, because their power is just 1. Okay? But what does that tell me? Well, this tells me it's just going to go through the graph. This tells me that I expect to bounce at there. Now, we can include this with end behavior as well, right? What we see here is we see that if this is, sorry, plus or minus 1. If this is 1, that's negative 1, and this is 1, then we expect to get zeros there, there, and there. However, we also know that this should go up, right? And so, because this goes up, down, because of end behavior, right? Leading coefficient is negative, and it's the even degree, so it should be down and down. But using that, we then know that the graph would have to come up from here. It would have to go through here because of this, right? But then it would have to turn and come back to touch down here at some point, right? So then, however, we just touch it, but we don't cross, right? So it would be something like this. And then again, we have to go through. So this is roughly what the graph looks like. In other words, we have 3 turning points, and while only having three zeros, okay? So now let's have you try an example. Go ahead and try to figure out, find all the real zeros of f of x equal x cubed minus 12x squared plus 36x and their multiplicities, and then use that to try to roughly determine sort of what the graph looks like, just vaguely. And then use, and then also that should tell you something about the turning points. So on the count of 3, I'll reveal the solution. 1, 2, 3. So here we go through, we factor, and we get this factorization. Once we factor the polynomial, we notice that x equals 0 occurs one time, but then we have a twice repeated root, x minus 6. So x equals 0 has multiplicity 1, x equals 6 has multiplicity 2. And here we also say, oh, but let's look at the end behavior. The end behavior says it needs to start off down here and go up and then end up here. Well, we see because multiplicity 1 will go through the graph, multiplicity 2 will sort of bounce off the graph, just touching it. And so it should look roughly like this, okay? What that means is that we would have 2 turning points, right? Here and there. Okay. Another interesting fun fact here is an even degree polynomial has an odd number of turning points, and an odd degree polynomial has an even number of turning points. This isn't too hard to see if you look at the last 2 examples, and kind of makes logical sense. Because for an even degree polynomial, you would have that would need to be up and up or down down, which means anytime you create a turning point, you could have one turning point, or if you added a second one, you would have to add a third one to go back up to match your end behavior, or similarly with down down. Here you can similarly see with an odd degree, in order to go down one way, if you add a turning point, you'd have to add another turning point to be able to keep going up. So it would have to have an even number. For more practice with working with the zeros and their multiplicities, be sure to see pages 132 and 133 of the textbook and work the following problems. In our next video, we'll go ahead and talk a little bit more about sketching polynomial functions.